Imagine capturing the entire energy output of our sun. Every single photon, every burst of solar wind, every erg of power that has been streaming into empty space for 4.6 billion years. We're talking about harnessing 400 trillion watts of pure energy. That's more power than humanity has consumed in our entire existence, generated every single second. This is the promise of a Dyson Sphere, and today we're going to explore exactly how to build one. But here's what will shock you. The engineering challenges we face aren't just difficult, they're so staggering that they redefine what we think is possible. We're about to discover why building a Dyson Sphere requires dismantling entire planets, creating self-replicating robot swarms, and developing technologies that make our most advanced spacecraft look like stone tools. Before we dive into the construction process, let me give you a sense of scale that will make your head spin. The amount of material needed to build a Dyson Sphere around our sun would require roughly 100 times the mass of Jupiter. Think about that for a second. We would need to completely disassemble a planet larger than every other object in our solar system combined, then somehow transport all that material across 93 million miles of space and assemble it into a structure so large that Earth's entire orbit would fit inside it like a marble in a basketball. This isn't science fiction anymore. This is engineering on a scale that stretches our understanding of what civilization can achieve. We're going to walk through every step of this process, from the initial material gathering to the final power distribution systems that could supply energy to billions of worlds. And I'll show you why some of the smartest minds on Earth believe this isn't just possible but inevitable for any civilization that wants to survive and expand beyond their home planet. Now, prepare yourself. We begin. The story begins in 1960 with a physicist named Freeman Dyson who asked a deceptively simple question that would revolutionize how we think about advanced civilizations. Dyson realized that any technological society would eventually exhaust the energy resources of their home planet. Earth intercepts only about 1/billionth of the sun's total energy output. The rest streams uselessly into empty space. This led Dyson to propose something radical. What if we could build a structure around the sun itself to capture all that wasted energy? Dyson's original concept wasn't actually a solid shell. Despite what science fiction movies might show you, he envisioned what we now call a Dyson swarm, a loose collection of thousands or millions of solar collectors orbiting the sun at various distances. Each collector would operate independently, following its own stable orbit while collectively working to intercept and redirect stellar energy. This swarm approach offers massive advantages over a rigid shell design. Individual elements can be constructed, launched, and positioned independently, allowing for gradual construction over centuries rather than requiring the simultaneous assembly of an impossibly massive structure. But even a Dyson swarm presents challenges that make landing on Mars look like a weekend camping trip. Let's start with the most fundamental problem. Where do we get the materials? The material requirements alone are mind-boggling. We're looking at approximately 600 kilograms of material per square meter across a sphere with a radius of 93 million miles. That works out to roughly 2.98 times 10 to the 22nd kilograms of raw materials. To put this in perspective, that's about 100 times the mass of Jupiter, or roughly 6,000 times the mass of Earth. We would need silicon for photovoltaic cells, carbon for structural elements, and metals for frameworks and electronics. A rough estimate suggests we'd need about 2.09 times 10 to the 23rd grams of silicon, 1.04 times 10 to the 23rd grams of carbon, and another 1.04 times 10 to the 23rd grams of various metals. Here's where it gets interesting. Our solar system actually contains enough material for this project, but it's not sitting around waiting for us to use it. The asteroid belt contains about 2.8 times 10 to the 21st kilograms of material, spread across millions of individual objects. While this sounds like a lot, it's actually only about 4% of the Moon's mass. We'd need to mine virtually every asteroid in the belt, and that still wouldn't be enough. This brings us to the first shocking reality of Dyson Sphere construction. We would need to systematically dismantle entire planets. Mercury emerges as the prime candidate for complete planetary disassembly. It's the closest planet to the Sun, making transportation costs lower, and it has a high metal content perfect for construction materials. Mercury contains about 3.3 times 10 to the 23rd kilograms of material, which gets us much closer to our target. But dismantling a planet isn't like strip mining a mountain. We're talking about breaking apart an object held together by gravitational forces so strong they've compressed rock into near-metallic density at the core. The engineering challenges are staggering. We'd need massive excavation systems that could operate in the extreme environment near Mercury's surface, where temperatures reach 800 degrees Fahrenheit on the day side and drop to minus 300 degrees Fahrenheit at night. The excavation process would require fleets of robotic mining systems, each the size of a city block, equipped with fusion-powered drilling systems and electromagnetic mass drivers to launch material into space. These systems would need to operate continuously for decades, gradually reducing Mercury from a planet to scattered debris clouds orbiting the Sun. Even with Mercury's material, we'd still need additional resources from the gas giants. Jupiter, Saturn, Uranus and Neptune contain vast amounts of hydrogen and helium that could be processed through fusion reactions to create heavier elements needed for construction. This introduces another layer of complexity. We're not just mining solid materials anymore. We're talking about atmospheric processing on a planetary scale, using magnetic scoops and fusion reactors the size of continents to extract and refine gases into useful construction materials. The logistics of transporting all this material present their own nightmarish challenges. We're looking at moving billions of tons of material across distances measured in hundreds of millions of miles. Chemical rockets are completely inadequate for this task. We'd need to develop new propulsion systems, probably based on fusion or antimatter technology, capable of accelerating massive cargo loads to significant fractions of the speed of light. But here's where the engineering gets truly revolutionary. The scale of construction makes traditional manufacturing approaches completely impossible. No human-operated factory could produce components for a Dyson Sphere. The solution lies in self-replicating manufacturing systems, often called von Neumann machines after the mathematician who first described them. These aren't just robots that build things. These are robots that can build copies of themselves, creating an exponentially growing workforce that can tackle projects on truly astronomical scales. The concept is elegantly simple. You create a seed unit, essentially a self-contained factory capable of gathering raw materials and producing an exact copy of itself. Deploy this unit to an asteroid or planetary surface rich in materials, and it begins the replication process. The first generation produces 2 units. The second generation produces 4. The third produces 8. Within just 30 generations, you have over 1 billion manufacturing units. Within 60 generations, you have more manufacturing capacity than exists on Earth today. This exponential growth is the only way to achieve the scale needed for Dyson Sphere construction. Each replicator unit would be programmed with the complete blueprints for every component needed in the sphere, from massive structural elements to delicate photovoltaic cells to sophisticated power management systems. The units would communicate with each other through quantum-encrypted channels, coordinating their activities across the entire solar system to ensure efficient resource allocation and construction sequencing. But self-replicating machines introduce risks that keep engineers awake at night. What happens if the replication programming develops errors? What if the machines decide they have better uses for the solar system's material than building a Dyson Sphere? These aren't abstract concerns. Any self-replicating system must include multiple layers of safeguards to prevent runaway replication or goal modification that could consume the entire solar system. The safeguards would need to be built into the fundamental architecture of the replicators. Each unit would have hard-coded limits on the number of copies it can produce. Replication would require authorization codes from multiple independent systems. Most importantly, the replicators would be designed with built-in obsolescence, automatically shutting down after completing their assigned tasks or after a predetermined time limit. Once we have our exponentially growing workforce and our material sources identified, we can begin the actual construction process. This is where the engineering challenges shift from logistics to precision assembly on an unprecedented scale. The construction would begin with the deployment of positioning satellites throughout the solar system. These satellites would use laser interferometry to create a three-dimensional coordinate system with accuracy measured in millimeters across distances of hundreds of millions of miles. Every component of the Dyson Sphere would need to be positioned with this level of precision to ensure proper orbital mechanics and energy collection efficiency. The first components to be constructed would be the foundation elements, massive structural frameworks that define the basic geometry of the sphere. These frameworks would be assembled from carbon nanotube composites and metallic glass alloys, materials that can maintain structural integrity under the extreme temperature variations and radiation environment near the Sun. Each framework element would be roughly the size of a small country, yet would need to be manufactured to tolerances measured in centimeters. The manufacturing process would take place in zero-gravity construction facilities positioned throughout the solar system, each facility capable of producing framework elements at a rate of several per day. As the framework takes shape, the next phase involves installing the energy collection systems. This is where the project's true purpose becomes apparent. We're not just building a structure, we're creating the largest power plant ever conceived. The energy collection systems would consist of billions of individual photovoltaic panels, each the size of a football field, arranged in hexagonal patterns across the sphere's surface. But these aren't ordinary solar panels. They're constructed from advanced materials like perovskite silicon tandems and concentrated photovoltaic systems that can achieve energy conversion efficiencies approaching 50%. The panels must be designed to operate in the extreme environment near the Sun, where radiation levels would instantly destroy conventional electronics and temperature variations could span hundreds of degrees within minutes. Each panel incorporates its own radiation shielding, thermal management systems, and self-repair mechanisms that can fix damage from micrometeorite impacts or solar flares. But collecting the energy is only half the challenge. We need to distribute it to useful locations throughout the solar system. This requires a power transmission system operating on a scale never before attempted. The power distribution system would use a combination of microwave and optical power beaming technologies to deliver energy across interplanetary distances. Massive transmitter arrays positioned across the sphere's surface would convert collected solar energy into highly focused beams that can be received by stations throughout the solar system. Each transmitter array would be the size of Manhattan, equipped with adaptive optics systems that can maintain beam focus across distances of billions of miles. The beams themselves would carry power levels measured in terawatts, enough energy to supply entire civilizations while remaining safe for space travel through sophisticated beam steering technology that automatically shuts down when spacecraft cross the transmission paths. The receivers scattered throughout the solar system would be equally impressive. These structures, called rectifying antennas or rectennas, would convert the incoming microwave energy back into usable electricity with efficiency rates exceeding 90%. Each receiver station would be capable of handling power loads that dwarf the output of entire nuclear power plants, distributing energy through superconducting transmission lines to planets, space habitats, and industrial facilities across the solar system. But here's where the engineering challenges become truly mind-bending. A Dyson sphere isn't a static structure. It's a dynamic system that must maintain perfect orbital mechanics while constantly adjusting to changing conditions. The gravitational forces acting on different parts of the sphere vary dramatically based on their distance from the Sun and their position relative to other massive objects in the solar system. Each section of the sphere must maintain its own independent orbit while remaining properly positioned relative to every other section. This requires a control system of staggering complexity, with millions of individual orbital adjustment engines distributed across the sphere's surface. These engines would use ion propulsion technology powered by the sphere's own energy collection systems to make constant micro-adjustments that keep the entire structure in perfect alignment. The control system would need to process gravitational data from throughout the solar system in real time, calculating the complex interactions between the sphere sections, planets, moons, and asteroids. The computational requirements are astronomical, requiring quantum computing systems distributed throughout the structure, each capable of processing calculations that would take our most powerful current supercomputers centuries to complete. Navigation through this system presents its own unique challenges. Space travel within a completed Dyson sphere would require entirely new approaches to trajectory planning. Traditional orbital mechanics assume empty space with predictable gravitational influences. Inside a Dyson sphere, spacecraft would navigate through a complex maze of massive structures, each creating its own gravitational effects and casting shadows that could affect solar-powered vessels. The sphere would need built-in transportation corridors, carefully designed gaps in the structure that allow for efficient movement of personnel and cargo between different sections. These corridors would be equipped with their own navigation beacons and traffic control systems, managed by artificial intelligence networks that can coordinate the movement of thousands of vessels simultaneously. Maintenance of a Dyson sphere introduces challenges that make maintaining the International Space Station look trivial. We're talking about a structure with a surface area millions of times larger than Earth, operating in one of the harshest environments in the solar system. Every component faces constant bombardment from solar radiation, micrometeorites, and charged particles that gradually degrade materials and electronics. The maintenance system would rely heavily on the same self-replicating technology used for construction, but adapted for repair and replacement operations. Specialized maintenance robots would patrol every section of the sphere, equipped with advanced sensors that can detect problems before they become critical failures. These robots would carry raw materials and manufacturing equipment, allowing them to produce replacement components on site rather than waiting for parts to be shipped across interplanetary distances. The most challenging maintenance operations would involve replacing entire sections of the sphere while maintaining structural integrity and power generation. This would require sophisticated load balancing systems that can temporarily redistribute structural stresses while sections are offline for replacement. The process would be like performing heart surgery on a patient while they're running a marathon, except the patient is larger than Earth's orbit and the surgery involves replacing components the size of continents. Environmental hazards present another layer of complexity that engineers must address. Solar flares can release energy equivalent to billions of nuclear weapons, creating electromagnetic pulses that could disable entire sections of the sphere's control systems. The structure would need comprehensive shielding systems, including magnetic field generators that can deflect charged particles and radiation-hardened electronics that can continue operating during extreme solar weather events. Asteroid impacts, while rare, pose catastrophic risks to a structure of this size. The sphere would incorporate a distributed asteroid detection and deflection system using the same power-beaming technology designed for energy transmission to vaporize or redirect incoming objects before they can cause damage. The system would need to track millions of objects simultaneously, calculating impact probabilities and automatically initiating deflection procedures without human intervention. The thermal management challenges are equally daunting. Different sections of the sphere receive vastly different amounts of solar energy based on their position and orientation. The sun-facing surfaces could reach temperatures exceeding 1000 degrees Celsius, while sections in shadow could drop to near absolute zero. This creates massive thermal stresses that could tear the structure apart if not properly managed. The solution involves an intricate network of heat pipes and thermal radiators that can transfer excess heat from hot areas to cold areas, maintaining relatively stable temperatures throughout the structure. These thermal management systems would be integrated into the sphere's basic architecture, with heat pipes running through every major structural element and radiators distributed across both the inner and outer surfaces. But perhaps the most fascinating aspect of Dyson Sphere engineering is how it would transform human civilization itself. The construction process would require international cooperation on a scale never before attempted, with resources and expertise contributed by every nation on Earth. The project would likely take several centuries to complete, requiring sustained commitment across dozens of generations. The economic implications are staggering. The construction cost would exceed the current gross domestic product of Earth by factors of millions. Traditional economic models become meaningless when dealing with projects of this scale. We would need entirely new approaches to resource allocation, labor organization, and risk management that account for the multi-generational timeline and astronomical scope of the undertaking. The social implications are equally profound. The construction workforce would include millions of people living and working in space for their entire careers. These communities would develop their own cultures, languages, and social structures adapted to life in zero gravity and the unique environment of interplanetary space. They would be pioneers of a new branch of human civilization, as different from Earth-based society as maritime cultures are from desert nomads. The technology developed for Dyson Sphere construction would revolutionize every other aspect of human civilization. The advances in materials science, robotics, energy systems, and manufacturing would solve countless problems on Earth while opening up possibilities we can barely imagine. The same self-replicating systems used to build the sphere could be applied to terraforming projects, space habitat construction, and interstellar exploration missions. Perhaps most importantly, the energy output of a completed Dyson sphere would eliminate scarcity as a driving force in human affairs. With access to the sun's entire energy output, humanity could power any conceivable project, from massive climate engineering efforts to the construction of additional megastructures throughout the solar system. We could build space habitats that dwarf planets, accelerate particles to near light speed for interstellar communication, or even begin the process of stellar engineering that could extend the sun's lifespan by billions of years. The completion of a Dyson sphere would mark humanity's transition from a planetary species to a true spacefaring civilization with the energy resources needed to expand throughout the galaxy and beyond. It would represent the ultimate expression of human engineering capability and our species' determination to transcend the limitations of our cosmic environment. But we're not there yet. The challenges we've explored represent just the beginning of what would be required to make this vision reality. In our next section, we'll dive deeper into the specific technologies that would make Dyson Sphere construction possible, from the quantum computers needed to manage the project to the exotic propulsion systems that could transport materials across interplanetary distances. We'll also explore the alternatives to traditional sphere designs and examine why some engineers believe swarm configurations might be more practical than solid structures. The journey from concept to construction is far from over, and the most fascinating engineering challenges still lie ahead. The quantum computing requirements alone would push our technology beyond anything we can currently imagine. Managing a Dyson Sphere isn't like operating a power plant or even a space station. We're talking about coordinating millions of independent components, each one larger than most cities, all while maintaining perfect orbital synchronization across distances that span the entire solar system. Think about the computational challenge for just a moment. Every component needs to know its precise position relative to every other component. The gravitational influences change constantly as planets move through their orbits. Solar radiation pressure varies based on the sun's activity cycles. Each section must adjust its trajectory thousands of times per day to maintain proper spacing and energy collection angles. The quantum computers managing this system would need processing power measured in qubits numbered in the billions. Current quantum computers barely reach a few hundred qubits. We're talking about a computational leap comparable to going from an abacus to a modern supercomputer. These quantum systems would be distributed throughout the sphere itself, with redundant networks ensuring that the loss of any single computing node couldn't compromise the entire structure. But here's where it gets really wild. The communication delays across a Dyson Sphere create problems that don't exist in any current engineering project. Light takes over 10 minutes to travel from one side of Earth's orbit to the other. When you're coordinating maintenance operations or emergency responses across that distance, 10 minutes might as well be eternity. The sphere's control systems would need to operate with a level of autonomous intelligence that approaches artificial consciousness. Each major section would require its own artificial intelligence capable of making complex decisions without waiting for instructions from central command. These AI systems would need to understand structural engineering, orbital mechanics, materials science, and emergency response protocols. They would essentially become the digital equivalent of city mayors, each responsible for managing their section while coordinating with neighboring regions. The manufacturing revolution required for Dyson Sphere construction would make the Industrial Revolution look like a minor workshop upgrade. We're not just talking about scaling up existing production methods. We need entirely new categories of manufacturing technology that can operate in the vacuum of space while producing components with precision measured in millimeters across structures spanning millions of miles. The key breakthrough would be continuous space-based manufacturing using materials harvested directly from asteroids and planets. Instead of mining materials, shipping them to Earth, processing them in factories, and then launching finished products back into space, the entire production cycle would happen in zero gravity. Raw asteroids would enter one end of massive orbital foundries and emerge as finished Dyson Sphere components. These space foundries would be marvels of engineering in their own right. Picture manufacturing facilities the size of Manhattan, equipped with fusion reactors for power, particle accelerators for materials processing, and assembly lines that stretch for hundreds of miles. The facilities would use magnetic levitation to manipulate materials without physical contact, preventing contamination and allowing for precision that's impossible under Earth's gravity. The assembly process itself would revolutionize how we think about construction. Instead of building from the ground up, Dyson Sphere components would be assembled in three-dimensional space using swarms of construction robots. These robots would work like a coordinated dance, each one knowing its role in positioning and connecting massive structural elements that could weigh millions of tons. The robots would use a combination of ion thrusters and reaction wheels for precise positioning, with magnetic grappling systems for handling metallic components and specialized adhesive systems for joining materials. Each robot would be equipped with sensors capable of measuring distances to nanometer precision, ensuring that components fit together perfectly despite being manufactured in different locations across the solar system. But the most mind-bending aspect of the construction process would be the timeline coordination. Different sections of the sphere would be under construction simultaneously at locations separated by hundreds of millions of miles. The manufacturing schedules would need to account for the orbital mechanics of both the construction sites and the final installation locations. Imagine trying to coordinate a project where some components take 6 months to build, others take 2 years, and the delivery time between manufacturing and installation varies from weeks to years depending on planetary alignments. The project management software would need to track millions of components through production cycles that span decades, automatically adjusting schedules based on changing solar system dynamics. The transportation infrastructure required to support construction would dwarf anything humanity has ever built. We would need cargo vessels capable of carrying loads measured in millions of tons across interplanetary distances. These ships would be more like mobile space stations than traditional spacecraft, equipped with their own manufacturing facilities, living quarters for crews, and defensive systems to protect against micrometeorite impacts. The propulsion systems for these cargo haulers would need to achieve specific impulse values far beyond chemical rockets. Nuclear thermal propulsion might work for the initial phases, but the massive cargo requirements would eventually demand fusion rockets or even antimatter propulsion systems. These engines would produce thrust levels measured in meganewtons while maintaining fuel efficiency that allows for round trips between planets without refueling. The logistics network would require permanent infrastructure throughout the solar system. Fuel depots positioned at gravitational balance points would allow cargo vessels to refuel during long journeys. Communications relay stations would maintain contact between Earth and construction sites, even when planets are on opposite sides of the Sun. Emergency rescue stations would be positioned along major shipping routes to assist vessels experiencing mechanical failures or other emergencies. The safety protocols for Dyson Sphere construction would need to account for hazards that don't exist in any current industrial operation. Workers would be operating in environments where the nearest safe haven might be millions of miles away. Rescue operations would need to account for orbital mechanics that could make immediate assistance impossible even if help is available. Emergency response plans would need to address scenarios ranging from equipment failures to solar storms to asteroid impacts. Each major construction site would maintain emergency supplies sufficient to support its entire workforce for months without resupply. Escape pods would be equipped with long-range propulsion systems capable of reaching safe harbors even if the main construction facility is completely destroyed. The radiation environment near the Sun presents challenges that make nuclear reactor safety look straightforward. Solar radiation levels at the construction sites would be lethal to unprotected humans within minutes. All work would need to be performed by robots or by humans in heavily shielded environments. The shielding requirements would be so extreme that work suits would essentially be miniature spacecraft, complete with life support systems, radiation shielding, and emergency propulsion. But the radiation hazard goes beyond immediate human safety. The intense solar radiation would gradually damage electronic components, requiring constant replacement of sensitive systems. The sphere's control electronics would need to be radiation hardened to levels far beyond anything currently available. Some systems might need to be positioned behind massive radiation shields, or even relocated to safer distances from the Sun. The thermal management challenges would create engineering problems that push the boundaries of materials science. components facing the sun would experience temperatures hot enough to melt steel, while components in shadow would face temperatures approaching absolute zero. The thermal expansion and contraction would create stresses that could tear apart conventional materials. The solution would require materials that simply don't exist yet. We would need structural alloys that maintain strength across temperature ranges spanning over 1,000 degrees. Thermal expansion joints would need to accommodate dimensional changes measured in kilometers while maintaining perfect structural integrity. Heat pipes capable of transferring gigawatts of thermal energy would be distributed throughout the structure like a circulatory system. The sphere's outer surface would incorporate adaptive thermal control systems that could adjust their heat rejection properties based on local conditions. These systems might use electrochromic materials that change color based on electrical signals, or mechanical louvers that can open and close to control radiative heat transfer. The control systems would need to respond to thermal changes within seconds to prevent structural damage. Quality control for Dyson Sphere construction would require inspection systems operating on a scale never before attempted. We're talking about inspecting welds across structures that span millions of miles, checking the alignment of components positioned with millimeter precision, and verifying the integrity of electrical systems carrying power loads measured in terawatts. Automated inspection systems would use advanced sensors including X-ray imaging, ultrasonic testing, and electromagnetic field mapping to detect flaws that could compromise structural integrity. Flying inspection drones would patrol the construction sites continuously, equipped with artificial intelligence systems capable of identifying potential problems before they become critical failures. The inspection data would be processed by machine learning algorithms trained to recognize patterns indicating material fatigue, manufacturing defects, or installation errors. These systems would need to account for the unique stresses and environmental conditions of space-based construction while maintaining inspection standards that exceed anything used in terrestrial construction projects. But perhaps the most fascinating aspect of Dyson Sphere engineering would be the backup systems and redundancy measures. A structure this large and complex would need multiple layers of backup systems to ensure that no single failure could compromise the entire project. The redundancy requirements would exceed those of nuclear power plants, space missions, and military systems combined. Every critical system would have at least 3 independent backups, each using different technologies to avoid common mode failures. Power distribution would use multiple independent networks with automatic load balancing that could route energy around damaged sections. Communication systems would include quantum entanglement networks that provide instantaneous communication across any distance, unaffected by solar interference or equipment failures. The structural redundancy would be built into the sphere's basic architecture. Each major section would be capable of supporting its neighbors if adjacent sections experience failures. Load-bearing elements would be distributed throughout the structure so that the loss of any single component wouldn't create cascading failures that could bring down entire regions of the sphere. Emergency protocols would address scenarios ranging from minor equipment failures to catastrophic events like solar superflares or large asteroid impacts. The sphere would maintain emergency reserves of materials, energy, and personnel positioned throughout the structure. Evacuation plans would account for the possibility of having to abandon entire sections while maintaining the integrity of the remaining structure. The environmental monitoring systems would track thousands of variables continuously, from radiation levels and temperature gradients to structural stresses and power distribution loads. Artificial intelligence systems would analyze this data in real time, identifying trends that could indicate developing problems problems and automatically initiating corrective actions before human operators even become aware of the issues. But the most revolutionary aspect of Dyson Sphere construction would be how it transforms our understanding of what's possible through engineering and human cooperation. This project would require sustained collaboration across centuries, with each generation building on the work of those who came before while laying the foundation for those who will follow. The knowledge management systems would need to preserve technical expertise across generational transitions, ensuring that critical engineering knowledge doesn't get lost as project personnel retire or die. The documentation would need to account for technology changes that could make current systems obsolete while maintaining compatibility with legacy components that can't be replaced. The project would create entirely new fields of engineering that don't currently exist. Stellar-scale structural engineering would become a recognized discipline with its own universities, professional societies, and certification programs. Interplanetary logistics would evolve from a theoretical concept to a practical field with standardized procedures and specialized equipment. The social infrastructure supporting the project would be as complex as the technical infrastructure. Entire civilizations would grow up around the construction sites, with their own governments, economies, and cultural traditions. These communities would need to maintain Earth-based human values while adapting to environments that are fundamentally different from anything in human evolutionary history. The economic systems would need to operate across timescales that exceed the lifespan of any current economic institution. Investment and planning horizons would stretch across centuries, requiring new approaches to resource allocation and risk management. The project would probably need to operate outside traditional market mechanisms, using planned economy principles adapted for the unique requirements of megascale construction. But the ultimate payoff would justify every challenge we've discussed. A completed Dyson Sphere would provide humanity with energy resources that exceed our current consumption by factors of billions. This energy abundance would eliminate scarcity as a driving force in human civilization while providing the power needed for projects that currently exist only in science fiction. We could terraform entire planets, build space habitats that house billions of people, or even begin engineering projects that could extend the sun's lifespan or move our entire solar system to avoid cosmic hazards. The Dyson Sphere would be just the beginning of humanity's transformation from a planetary species to a true galactic civilization. The construction process itself would advance human technology across every field imaginable. The materials, science, robotics, artificial intelligence, and manufacturing innovations would solve countless problems while opening possibilities we can't even imagine yet. We would emerge from the project as a completely different species, with capabilities that would seem magical to our current level of civilization. The timeline for completing this project stretches beyond anything humans have ever attempted. We're not talking about a construction project measured in years or even decades. A Dyson Sphere would require sustained effort across multiple centuries, possibly millennia. To put this in perspective, the Great Wall of China took over 2,000 years to complete, and that's a structure you can walk across in a few hours. We're proposing to build something with a surface area 600 million times larger than Earth. This temporal scale creates challenges that go far beyond engineering. How do you maintain institutional knowledge across 50 generations of workers? How do you ensure that construction standards remain consistent when the people who designed the original specifications have been dead for centuries? These aren't abstract philosophical questions. They represent fundamental project management challenges that could determine success or failure. The solution lies in creating what engineers call institutional immortality. Every aspect of the project would need to be documented with redundancy levels that exceed anything we've ever attempted. Technical specifications, manufacturing procedures, quality control standards, and safety protocols would be stored in multiple formats across distributed locations throughout the solar system. But documentation alone isn't enough. We would need to establish educational institutions dedicated entirely to Dyson Sphere construction, universities that exist for the sole purpose of training each new generation of workers in technologies that might not change for centuries. These institutions would become the keepers of technical knowledge, ensuring that critical expertise survives even if entire civilizations rise and fall during the construction period. The workforce management challenges boggle the mind. At peak construction, the project might employ 100 million people working at sites distributed across the entire solar system. These workers would include everything from asteroid miners to precision assembly technicians to artificial intelligence programmers. Many would spend their entire careers in space, never setting foot on Earth after their initial training. Managing this workforce requires creating entirely new categories of human resources systems. Traditional employment models break down when your workplace might be 500 million miles from the nearest manager, and communication delays measure in hours rather than seconds. Each major construction site would need autonomous management systems capable of handling everything from work scheduling to disciplinary actions without constant oversight from Earth. The supply chain complexity makes current global logistics look like a corner grocery store. Every construction site needs a constant flow of raw materials, manufactured components, replacement parts, food, water, and personnel. The delivery schedules must account for orbital mechanics that change constantly as planets move through their orbits. Consider the challenges of delivering a critical component from a manufacturing facility near Jupiter to an installation site near Mercury. The journey might take anywhere from 2 to 7 years depending on planetary alignments. The component must be manufactured years before it's needed, stored in conditions that preserve its functionality across interplanetary distances, and delivered with timing precision that accounts for the complex gravitational dynamics of the entire solar system. The quality assurance protocols would need to catch manufacturing defects across supply chains spanning billions of miles. A faulty component manufactured near Saturn might not reveal its defect until installation near the Sun, where replacement could take decades. The inspection systems would need to achieve reliability levels that exceed aerospace standards, while operating at scales that dwarf any current manufacturing operation. Risk management for a project of this scope requires thinking about failure modes that don't exist in any current engineering context. What happens if a solar superstorm damages control systems across 30% of the sphere? How do you handle the logistics failure that leaves construction crews stranded for years without resupply? These scenarios demand contingency planning that accounts for possibilities no human organization has ever faced. The backup systems would need their own backup systems. Critical components would be manufactured in multiple copies and stored at distributed locations throughout the construction zone. Emergency supplies would be positioned to support isolated work crews for extended periods. Evacuation procedures would account for the possibility that rescue might take years to arrive. But the most mind-bending aspect of the risk analysis involves cascading failures that could threaten the entire project. The loss of a major manufacturing facility could delay construction by decades. A navigation error that results in component collisions could create debris fields that make entire regions of space too dangerous for construction work. These low-probability, high-impact events require insurance and contingency funding on scales that exceed the gross domestic product of entire planets. The financial engineering required to fund this project would revolutionize how we think about economics and investment. We're talking about capital requirements that exceed current global wealth by factors of millions. Traditional investment models become meaningless when payback periods stretch across centuries and the initial investment exceeds the economic output of entire civilizations. The funding mechanisms would probably require new forms of economic organization that blend elements of government funding, private investment, and resource taxation. Some economists propose creating Dyson bonds, investment instruments with maturity periods measured in centuries, backed by the promise of energy revenues from the completed structure. But the economic benefits begin long before completion. The technology development required for construction would create countless spin-off innovations with immediate commercial applications. The materials science advances alone would revolutionize manufacturing, construction, and transportation across human civilization. The robotics and artificial intelligence systems would transform every industry, while the manufacturing techniques would make current production methods look primitive. The job creation effects would be unprecedented. Entire new industries would emerge to support construction activities. Space-based mining, interplanetary transportation, orbital manufacturing, and stellar engineering would become major economic sectors employing millions of people. These industries would continue growing throughout the construction period, creating economic benefits that justify the investment long before the sphere becomes operational. The environmental impact assessment for this project would require entirely new categories of analysis. We're proposing to alter the fundamental energy balance of the solar system by intercepting a significant portion of the sun's output. This could affect everything from planetary climates to the behavior of comets and asteroids throughout the solar system. The sphere's construction would create the largest artificial structures ever built, potentially affecting the orbital dynamics of planets and moons. The mining operations required to gather materials would alter the composition of the asteroid belt and could affect the long-term stability of planetary orbits. These changes would need to be modeled with precision that exceeds our current understanding of celestial mechanics. But the environmental benefits could outweigh the costs. The energy abundance provided by a completed sphere would eliminate the need for fossil fuel consumption, nuclear waste generation, and other forms of environmental destruction associated with current energy production. The project could enable massive environmental restoration efforts on Earth while providing clean energy for terraforming projects throughout the solar system. The sphere's construction would also create opportunities for environmental engineering on planetary scales. The precise control of energy distribution could allow for climate modification projects that restore damaged ecosystems or create entirely new biospheres on previously uninhabitable worlds. We could transform Mars into a garden planet or create artificial environments that support Earth-based life in the outer solar system. The international cooperation required for this project would necessitate new forms of global governance that transcend current political boundaries. No single nation could possibly fund or manage a project of this scope. Success would require unprecedented coordination between governments, corporations, and international organizations. The project would probably require establishing a new category of international institution, something like a planetary construction authority with powers that exceed current international organizations. This authority would need the ability to allocate resources on a global scale, coordinate activities across multiple governments, and make decisions that affect the entire human species. The legal frameworks would need to address questions that don't exist in current international law. Who owns the energy output of a structure built with resources from multiple planets? How do you establish property rights for structures larger than entire solar systems? What legal system governs disputes between workers who might be separated by hundreds of millions of miles? The space law implications are staggering. Current space treaties assume relatively small-scale activities like satellite launches and space station operations. A Dyson Sphere would require completely new legal frameworks that address resource extraction rights, construction permissions, and operational authorities for structures that span the entire solar system. The sphere would also create new categories of citizenship and governance. People born and raised in space-based construction communities would have cultural and legal ties that transcend Earth-based nationality. These communities might develop their own forms of government adapted to the unique requirements of space-based living, creating political entities that exist independently of terrestrial nations. The cultural implications of this project extend far beyond politics and law. The construction process would create the first truly spacefaring human civilization, with millions of people living their entire lives in environments completely different from Earth. These communities would develop their own languages, customs, art forms, and social structures adapted to zero gravity and the unique conditions of interplanetary space. The psychological effects of living in such an environment would reshape human nature itself. People who grow up in space develop different spatial reasoning abilities, social interaction patterns, and even physical characteristics adapted to zero gravity. After several generations, space-based humans might become as different from Earth humans as maritime cultures are from desert nomads. The educational systems required to support these communities would need to prepare students for careers and life experiences that have no precedent in human history. Engineering curricula would include stellar-scale construction techniques. Navigation courses would cover interplanetary trajectory planning. Social studies would address the governance of communities distributed across billions of miles of space. The religious and philosophical implications challenge our fundamental understanding of humanity's place in the universe. Building a Dyson Sphere represents the ultimate expression of human technological capability, demonstrating that we can literally reshape the cosmos to serve our purposes. This level of engineering capability would place humanity among the gods of ancient mythology, with the power to create or destroy on scales that affect entire solar systems. But this power would come with equally unprecedented responsibilities. The decisions made during construction would affect not just current human civilization, but potentially thousands of future generations. The environmental choices would determine the long-term habitability of the solar system for any species that might evolve or be introduced in the future. The sphere's completion would mark humanity's transition from a planetary species to something entirely new. We would become the first known civilization capable of harnessing the complete energy output of a star, placing us on the Kardashev scale as a Type II civilization with capabilities that approach the realm of cosmic engineering. This transformation would open possibilities that currently exist only in the most ambitious science fiction. We could begin projects like moving the entire solar system to avoid future cosmic hazards, engineering the sun to extend its lifespan, or even creating artificial stars to expand the habitable zone throughout the galaxy. The Dyson Sphere would serve as humanity's graduation from a species constrained by the energy limitations of a single planet to a civilization capable of undertaking projects on truly galactic scales. It would represent the ultimate vindication of human intelligence, creativity, and determination to transcend the limitations imposed by our cosmic environment. But we're still centuries away from beginning such a project. The technological, economic, and social prerequisites represent challenges that will require sustained effort across multiple generations just to reach the point where construction could begin. The journey from our current capabilities to Dyson Sphere construction represents one of the greatest adventures in human history, requiring advances in science and engineering that will fundamentally transform what it means to be human. The next phase of our exploration will examine the alternative approaches to stellar energy capture that might be more practical than traditional sphere designs. We'll discover why some engineers believe that swarm configurations offer advantages that solid spheres cannot match, and we'll explore the exotic technologies that could make interstellar versions of these megastructures possible. The most fascinating aspects of Dyson Sphere engineering are yet to come. The alternative configurations represent perhaps the most crucial decision in the entire project. While science fiction has popularized the image of a solid shell completely enclosing the sun, the engineering reality demands a more sophisticated approach. The choice between swarm, ring, and partial sphere designs will determine not just the construction timeline, but the fundamental character of human civilization for millennia to come. A Dyson swarm offers the most practical path forward, consisting of millions of independent collectors following their own stable orbits around the Sun. Each collector would be roughly the size of Manhattan, equipped with advanced photovoltaic arrays and attitude control systems that maintain optimal positioning for energy collection. The beauty of this approach lies in its modularity. Construction can begin with just a few collectors, gradually building capacity over decades while generating immediate returns on investment. The orbital mechanics of a swarm configuration create fascinating possibilities that solid spheres cannot match. Individual collectors can be positioned at different distances from the Sun, allowing for specialized designs optimized for specific energy collection requirements. Collectors in close solar orbits might focus on high-intensity energy harvesting, while those positioned farther out could specialize in broad-spectrum collection or serve as relay stations for power transmission to the outer planets. But the swarm approach introduces coordination challenges that push control systems beyond anything we've ever attempted. Millions of collectors must maintain precise spacing to avoid collisions while adjusting their positions to account for gravitational perturbations from planets, asteroids, and solar wind pressure. The control algorithms would need to process orbital data for every collector simultaneously, calculating collision probabilities and trajectory adjustments in real time across a system spanning hundreds of millions of miles. Each collector would require its own artificial intelligence system capable of autonomous operation for extended periods. Communication delays across the swarm mean that central control becomes impossible for time-critical decisions. When a collector detects an incoming asteroid or experiences a system failure, it must respond immediately without waiting for instructions that might take hours to arrive. These AI systems would essentially become the digital equivalent of spacecraft pilots, each responsible for navigating their collector through the complex gravitational environment while maintaining optimal energy collection efficiency. The power transmission systems for a swarm configuration would revolutionize how we think about energy distribution. Instead of trying to transmit power from a single massive source, the swarm would create a distributed energy network with thousands of transmission points scattered throughout the inner solar system. This approach offers unprecedented redundancy and flexibility, allowing energy routing around damaged or offline collectors while maintaining continuous power delivery to consumers. The transmission technology itself would need to achieve precision that exceeds our current capabilities by orders of magnitude. Each collector would be equipped with steerable microwave or optical transmitters capable of maintaining focused beams across interplanetary distances. The beam pointing accuracy would need to be measured in microradians, equivalent to hitting a target the size of a dinner plate from a distance of 1,000 miles, while both the transmitter and receiver are moving at thousands of miles per hour. But here's where the engineering becomes truly revolutionary. The swarm configuration would enable energy collection strategies that are impossible with fixed structures. Collectors could be programmed to migrate toward regions of space with optimal solar conditions, following the sun's magnetic field variations or positioning themselves to avoid solar storms. During periods of high solar activity, collectors could retreat to safer distances, while during quiet periods they could move closer to maximize energy collection. The construction sequence for a swarm would begin with what engineers call seed collectors, the first generation of energy harvesting units that provide power for building subsequent generations. These initial collectors would be launched using conventional rockets, probably deployed at the L1 Lagrange point, where gravitational forces from Earth and the Sun create a stable platform for initial operations. The seed collectors would serve multiple functions beyond energy collection. They would act as navigation beacons for incoming construction materials, communication relays for coordinating the construction process, and manufacturing platforms for producing the specialized components needed for later collectors. Each seed collector would be equipped with 3D printing systems, materials processing equipment, and assembly robotics capable of producing copies of itself using raw materials delivered from asteroid mining operations. The exponential growth phase would begin once the seed collectors achieve self-sufficiency in materials and energy. The first generation produces enough power and materials to build 2 collectors. The second generation builds 4. The third builds 8. Within just 50 generations, the swarm could contain over a quadrillion collectors, enough to intercept a significant fraction of the Sun's total energy output. This exponential growth creates timing challenges that require precision planning across decades. The materials delivery schedules must account for the exponentially increasing demand while maintaining sufficient buffer stocks to prevent construction delays. The transportation infrastructure must scale up at the same exponential rate, requiring the simultaneous development of increasingly large cargo vessels and more efficient propulsion systems. Quality control during exponential growth phases presents unique challenges that don't exist in traditional manufacturing. Each generation of collectors must maintain the same construction standards as the previous generation, despite being built by increasingly automated systems with minimal human oversight. Manufacturing defects that appear in early generations could be replicated millions of times if not caught and corrected immediately. The solution involves what engineers call evolutionary quality control, where each collector generation incorporates improvements based on performance data from previous generations. Manufacturing tolerances are tightened based on failure analysis. Materials specifications are refined based on long-term durability testing. Control algorithms are updated based on operational experience. The swarm essentially evolves toward higher performance and reliability through controlled artificial selection. But the most fascinating aspect of swarm construction is how it would transform the inner solar system into a vast industrial complex. The space between Earth and the Sun would become filled with construction activities, transportation corridors, and manufacturing facilities on a scale that dwarfs any Earthbound industrial development. Entire regions of space would be dedicated to specific industrial functions, creating specialized zones for materials processing, component manufacturing, and final assembly. The asteroid belt would be transformed into the largest mining operation in human history, with thousands of robotic mining systems simultaneously extracting materials from millions of asteroids. The mining robots would use fusion-powered drilling systems to extract materials, magnetic separation systems to sort different elements, and mass drivers to launch processed materials toward manufacturing facilities throughout the inner solar system. The transportation network supporting this industrial complex would require cargo vessels operating on schedules that account for the constantly changing positions of planets and manufacturing facilities. The logistics algorithms would need to optimize cargo routing across a 3-dimensional transportation network where distances and travel times change continuously based on orbital mechanics. Fuel supply for this transportation network presents its own engineering challenges. The cargo vessels would require enormous amounts of propellant for interplanetary journeys, but launching fuel from Earth would be prohibitively expensive. The solution lies in establishing fuel production facilities throughout the solar system, using resources extracted from asteroids and planets to produce hydrogen, oxygen, and exotic propellants needed for advanced propulsion systems. The manufacturing facilities themselves would represent the pinnacle of automated production technology. These orbital factories would operate continuously for decades, producing millions of identical components with precision that exceeds anything achievable in terrestrial manufacturing. The quality control systems would use artificial intelligence to inspect every component, automatically adjusting manufacturing parameters to maintain optimal production standards. But perhaps the most mind-bending aspect of swarm construction is the maintenance and upgrade challenges. With millions of collectors distributed across hundreds of millions of miles, traditional maintenance approaches become completely impractical. The solution requires developing maintenance systems that can operate autonomously across interplanetary distances, diagnosing problems and implementing repairs without human intervention. The maintenance robots would need to be as sophisticated as the collectors themselves, equipped with advanced diagnostics, repair capabilities, and the ability to manufacture replacement components on site. These robots would patrol the swarm continuously, identifying collectors that need attention and performing repairs before minor problems become major failures. The upgrade process would be even more complex, requiring the systematic replacement of older collectors with improved designs while maintaining overall swarm functionality. The upgrade schedule would need to account for the operational lifetime of different collector generations while ensuring that power generation capacity never drops below critical levels needed to support ongoing construction activities. Component standardization becomes crucial for managing a swarm of this complexity. Every collector must use identical interfaces for power transmission, communication, and maintenance access. The standardization requirements would drive the development of universal design principles that remain valid across multiple generations of technological advancement, ensuring that collectors built decades apart can still work together seamlessly. Building a Dyson Sphere represents humanity's ultimate engineering challenge, demanding technologies that push every scientific discipline beyond its current limits. From dismantling entire planets to creating self-replicating manufacturing systems that span the solar system, we've explored engineering problems that make our greatest achievements look primitive by comparison. The material requirements alone dwarf the mass of Jupiter. The construction timeline stretches across centuries. The coordination challenges require artificial intelligence systems approaching consciousness itself. Yet the payoff transforms us from a planetary species into masters of stellar energy, capable of powering projects that currently exist only in our wildest dreams. The question isn't whether we can build it, but whether we're ready to become the kind of civilization that could.